So at the end of yesterday's class, we defined horizontal asymptotes. And to find a horizontal asymptote, we needed to take a limit to infinity, and then we needed to look in the negative direction, limit to negative infinity. So before doing specifically horizontal asymptote examples, let's do a couple limits as x goes to infinity. I was experimenting with a new kind of chalk, and well, I'm going to go back to the old kind. So evaluate each limit. There are going to be 3 in this example. We're going to see that to do all 3, we start the same way. So limit as x goes to infinity of 3x cubed plus 2x minus 1 over, let's do 4x cubed minus x. We're largely going to be looking at rational functions. And then later we'll put a square root in one of them and see how that changes the answer. Limit as x goes to infinity of, let's do 4x squared plus 2x all over 5x cubed minus 1, and then there will be part C. So we have a limit as x goes to infinity of a rational function here. And the process we're going to go through will work for any limit as x goes to infinity of a rational function. What we're going to do is look at the denominator and look at the degree of the denominator, the largest exponent in the denominator. And we're going to use that to figure out what we can multiply by, which will cause this to simplify. The largest exponent in the bottom of part A is 3. Because of that, the following multiplication will lead to a nice simplification. Multiply by 1. Multiplying by 1, of course, doesn't change it. But which 1 are we going to multiply by? 1 over x cubed divided by 1 over x cubed. And let's see how that simplifies. Limit as x goes to infinity, we still haven't taken a limit. Distribute this 1 over x cubed through the top, distribute it through the bottom. If you distribute it through the top, what do you get? Maybe I'll write this first step out. Distribute it through the top. You get 3x cubed over x cubed plus 2x over x cubed minus 1 over x cubed. Any questions about distributing that through the numerator? We will simplify each of those in a moment. And now we'll do the same thing with the denominator, 4x cubed divided by x cubed, and then negative x divided by x cubed. Now, why does this make this an easier limit to compute? Well, it may not be clear now, but it will become more clear when we reduce each fraction. Because 3x cubed divided by x cubed, the x cubes cancel, and you're left with just 3. 2x divided by x cubed, well, one of these x's is going to cancel with one of those x's, but that still leaves you with 2 of those 3 x's in that denominator. This is a 2, this exponent. And then negative 1 over x cubed, well, nothing's going to cancel that. Any questions about how the numerator simplified? Now, we still haven't taken a limit, so we still write the limit. But the denominator simplifies a little. 4x cubed divided by x cubed, x cubes cancel, you're left with 4. X over x cubed, again, one of those x's is going to cancel, so you're left with negative 1 over x squared. Now, is this limit easier to compute than the other ones? Well, it is, because we can do this using the algebraic limit laws, we can take the limit piece by piece. And what happens as x goes to infinity on each of these pieces? As x goes to infinity, as x goes to infinity, well, 3 doesn't change. What happens as x goes to infinity of 2 over x squared? Well, the denominator keeps getting larger. 2 stays the same. You divide 2 into larger and larger pieces, that'll get smaller and smaller, and it will go to 0. Similarly, for this last piece, negative 1 over x cubed, you divide negative 1 into larger and larger, or sorry, into smaller and smaller pieces, it'll go to 0. Another way of seeing these limits is by looking at a graph of 1 over x squared and noticing as x goes to infinity, 1 over x squared goes to 0 as x goes to infinity, and then multiply it by 2. That's not going to change. The fact that goes to 0, and similarly for 1 over x cubed. And then the denominator as x goes to infinity, 4 doesn't change, and 1 over x squared goes to 0. And this fraction now reduces to just 3/4. Any questions about this first one? Okay. So there are going to be 3 examples in this example. And then after this, I'm going to refer you to a document that I posted on Canvas. So we will reference back to this one, part A and part B, and part C. How about this next one? Well, we have 4x squared plus 2x over 5x cubed minus 1. The same first observation will work here. Meaning, in the previous one, we looked at the largest exponent on the denominator, and we used that to figure out what we can multiply by. Here, the largest exponent on the denominator is again a 3. So if we multiply by 1 over x cubed over itself, this will lead to a similar simplification. Now, in these, I am looking at the denominator and using that to figure out what we multiply by. There is a parallel argument using the numerator. Using the denominator is more standard and then in some way a little simpler than using the numerator. But what do we get when we distribute? Well, I'm going to jump over this middle step from part A and jump straight to this step. This step takes a lot of writing. 4x squared divided by x cubed, 2 of the x's cancel. We're left with 4 over x. 2x divided by x cubed, 1 of the x's will cancel. We're left with 2 over x squared. In the denominator, distribute x cubed through. 5x cubed divided by x cubed is just 5. And then we have negative 1 over x cubed. Any questions about that first step in simplification? So now as x goes to infinity, that piece goes to 0, 4 over x goes to 0, 2 over x cubed goes to 0, 5 remains unchanged, negative 1 over x cubed goes to 0, and this fraction 0 over 5 reduces to 0. Any questions about part B?
For the middle, you said 2 over x cubed. Is that 2 over x squared?
This one? Yeah, that's 2 over x squared. Did I say x cubed?
Yeah, okay.
2x divided by x cubed.
Okay.
X will cancel your over x squared. Any other questions about part B? Okay, so now we'll do part C, and we'll make an observation about parts A, B, and C. This other kind of chalk I use, the erasers don't work on, so I needed a cloth. The water doesn't evaporate quickly for me to use consistent. Part C, limit as x goes to infinity of what? Let's do 5x to the fifth minus 2x to the fourth, all over, how about 3x to the fourth plus 1. So we have this limit. The same first step will work. Look at the largest exponent on the denominator and multiply by 1 in the form of 1 over x to the largest exponent on the denominator. Here, the largest exponent on the denominator is 4. So multiply by 1 over x to the fourth. Divide by 1 over x to the fourth. And what do we get? Well, still a limit. Distribute x to the fourth through the top. You have 5 x's here, you have 4 x's here, 4 of them will cancel, 1 will remain, and the 5 will also remain. X to the fourth, negative 2x to the fourth, divided by x to the fourth, all those x's are going to cancel, and you just have a negative 2. How about in the bottom? 3x to the fourth divided by x to the fourth is just 3. 1 over x to the fourth is 1 over x to the fourth. Any questions about that first step in simplification? Okay, now how can we take this limit? Well, as x goes to infinity, let's do this in 2 steps. As x goes to infinity, how does 5x change? Well, 5x doesn't go to a number. 5x would be a line. As x goes to infinity, 5x would also go to infinity. So let's right here, just write that as a limit. How does negative 2 change as x goes to infinity? Well, it doesn't change. It stays negative 2. How does 3 change? 3 also doesn't change. But 1 over x to the fourth as x goes to infinity goes to 0. So we now have this limit. Any questions about that step in simplification? Okay. So how can we compute this limit? Well, could do it in 2 steps. You could reduce this fraction and then say it's a line with slope 5/3, y-intercept negative 2/3. I'm okay with just doing it in 1 step. And how do we get this? Well, as x goes to infinity, 5x goes to infinity. If you take 2 off of something that goes to infinity, that's not going to change it. And if you divide something which goes to infinity into 3 pieces, that will still go to infinity. So any questions about part C? I mean, that last step is a little informal in the treatment of infinity, but it's okay because it is nice to have in the back of your mind, if you take something which goes to infinity and subtract some finite number, that's not going to change it. And if you divide it by a positive number, that's not going to change it. So any questions about part C? Now let's look at parts A, B, and C. Well, let's look at the document I posted on Canvas. I think I posted it on Monday. It's called Limit to Infinity Theorem. So on this document on Canvas, there's a theorem which generalizes these three examples. You'll notice in part A, the answer was 3/4. And 3 and 4 happened to be, in part A, the coefficients on the largest exponent term in the numerator and denominator, and they both had exponent 3. So in part A, we had degree 3 divided by degree 3. And the limit wound up being the coefficient on that degree 3 term divided by the coefficient on the other degree 3 term. We had a 3x cubed divided by 4x cubed. And then the limit wound up being 3/4. And that argument generalizes when the degree on top is the same as the degree on the bottom. So this theorem, the first part of that piecewise function follows part A, because the degree of the top equal the degree on the bottom. Now, part B is still written. Part B, we had a degree 2 on top and degree 3 on the bottom. That limit wound up being 0 as x went to infinity, and that happens in general. The general proof uses this same type of argument, and notice here in the numerator, everything went to 0, the denominator went to a number. And that happens in general when the degree on the top is smaller than the degree on the bottom. Now, part C parallels the third result here, and that's a little more involved. Part C here, we wound up getting a positive infinity. Now, we could have gotten a negative infinity. If this were a -5, or if this were a -3, we would have wound up with a negative infinity. But you can use this result unless you're told not to. And the 4 examples at the bottom of that just illustrate, the first 2 parts, and then the last 2 illustrate the last part. So on a test, you may be asked for one of these to show all of your work. And if you are asked to show your work, you have to go through this process. If you're not asked to show your work, you can use the coefficient argument. Any questions about that? So on the homework, it doesn't say to show your work. It's almost definite that on exam 1, it will say show your work, in which case you'll have to go through one of these arguments. On the final, probably won't say to show your work. So any questions about that? So we've seen how we can compute limits as x goes to infinity. Our goal here was, well, one of our goals was to find horizontal asymptotes of a function. And to find a horizontal asymptote, we would need to look at the behavior as x went in the positive direction and the negative direction. So how can we compute a limit as x goes to negative infinity? Well, for most of them that we could see, that same argument will work. For some of them, it won't. Where to put the notes? Oh, these are them. So for some of them, that same argument will work. Largest exponent on the bottom, and distribute, a lot of things will go to 0. In some cases, it won't work, and we'll see one of those in a moment. I'll say in general, limits as x goes to negative infinity, I won't say I'll say are not the same. as limits as x goes to positive infinity. So those first three examples, if you took the limit as x goes to negative infinity, the same argument will work, but in general, that won't hold true. But there is something we can do to handle a limit as x goes to negative infinity. I'll write it here. To handle a limit as x goes to negative infinity, we will, so I'm going to finish this sentence in a moment. You'll probably, it's about 7 or 8 words. We will do something, and I'll illustrate what we'll do over here. So here we have a Cartesian plane. The limit as x goes to negative infinity considers the behavior as x goes in that direction. Looking for the words I used on this in my notes. Okay. The limit as x goes to negative infinity looks at x is going in that negative direction. What we can do is convert this behavior into a behavior as x goes to positive infinity. What can we do to make behavior in that direction happen in this direction? We know how to compute these limits as x goes to positive infinity. Well, what we can do is flip the function over the the y-axis. So the transformation, graph transformation, which transformation flips over the x-axis? Well, I'm going to introduce some notation. Right here we have x, and that's an arrow with like a bar on that side, a vertical bar. Well, if you replace all x's with a negative x, then that causes the function to flip over the y-axis, but in particular, the transformation replace all x's with negative x. This symbol in math is technically read maps to, M-A-P-S-T-O. But you can think of it as just take all x's, replace them with negative x. That transformation causes the behavior, well, it causes the function to flip over the x-axis. But in particular, what happens in that direction will now happen in that direction. So if we flip it over the x-axis, there's a flip over the y-axis, then the limit as x goes to negative infinity is now converted into a limit as x goes to positive infinity. And then we can compute that. So to finish the sentence, to handle a limit as x goes to negative infinity, we will convert it into a limit as x goes to positive infinity. We can then compute that as we did before. Any questions about that? That should be a colon at the end of this, not a period, because technically it's from that observation. So any questions about that? Okay, now to illustrate the computation as x, or the computation of the limit as x goes to negative infinity, let's do an asymptote example. So on yesterday, we found the vertical asymptotes for this function. So let's find horizontal asymptotes, what was this, 5 something? Not that one. 5x squared minus 4x is the bottom. So yesterday we found the vertical asymptotes of this, which were the lines, what, x equals 4/5 and x equals 0. So let's now find the horizontal asymptotes of this function. Now, we have two limits to consider. The limit as x goes to positive infinity, the limit as x goes to negative infinity. And, well, let's do the positive infinity one first. So first we'll notice this one doesn't say to show all your work. So for this one, I won't show all the work. I'll use the theorem. In the next one, we will show all the work. We have degree 2 on top, degree 2 on bottom. The limit as x goes to infinity is that number 2 divided by that number 5. Any questions about that first limit? Okay, so for the horizontal asymptotes, we do need to look at both limits. How can we compute this limit? Well, first, I will tell you there is a parallel theorem to that posted theorem for limits as x goes to negative infinity. If you're careful, you can use that. Odds are, question I asked won't be one like that. It would be more likely to be like the next example we do where they differ. But let's illustrate here the conversion into a limit as x goes to positive infinity. How can we convert this into a limit as x goes to positive infinity? Notice negative infinity, positive infinity. Replace all x's with negative x's. So we have 2. Replace all x's with negative x. Replace all x's with negative x. Replace all x's with negative x. And what does this simplify to? Well, it's a limit as x goes to positive infinity. Negative x squared is positive x squared, the negatives cancel. 3 doesn't change. This negative x squared is positive x squared. But in that last piece, we have negative 4 times negative x, which gives us 4x. And now we have degree 2 over degree 2. The limit here is again, as x goes to infinity, given by this coefficient divided by that coefficient. So what are the horizontal asymptotes? Well, we need both limits. They both happen to be the same. So y equals 2/5 is the horizontal asymptote. Now, in general, these two limits aren't going to be the same. In some examples, they will be the same. So any questions about that before we do one where they're not the same? Okay, so let's do one more. Let's do find the vertical and horizontal asymptotes of this function. This one will have 2 horizontal asymptotes. of what? Let's write it a little larger. Of f of x equals square root of 2x squared plus 5 divided by 4 minus 3x. So find the vertical and horizontal asymptotes. We're going to need, well, for the horizontal ones, we're going to need two limits. For the vertical ones, we're going to need to set the denominator equal to 0. Vertical ones are generally easier, so I usually do them first. Guess I'll write it down here. For the vertical asymptotes, remember, they'll occur where the denominator is 0. 4 minus 3x equals 0. Well, add 3x, divide by 3, or subtract 4, divide by negative 3. Either way, you get what? X equals 4/3. Any questions about the vertical asymptote? Okay, so let's do the horizontal asymptotes. Now, this is our first one with a square root as x goes to positive infinity. We will see the same first step will work. You just have to be a little careful with its simplification. What was the same first step? Well, look at the denominator. Largest exponent of the denominator is 1. Multiply everything by 1 over x. And what does this equal? Well, in the denominator, distributing the 4x through, you get distributing the 1 over x through, you get 4 over x minus 3. But what do you get in the numerator? Well, we can't just throw that x into the square root. Now, you can't get into a square root unless you have a square root yourself. But what we can do is rewrite that x using a square root, because x is the same for positive x as the square root of x squared. So in this numerator, what we can do is replace this x with the square root of x squared. That is still multiplying by 1. This numerator is the same as that denominator, but that square root will allow us to get into that other square root. And the simplification would then be 2x squared divided by x squared is 2. 5 divided by x squared is 5 divided by x squared. Any questions about that? Okay. Now, this limit, as x goes to infinity, well, using the limit laws, we can do this piece by piece. Law 7 tells us we can do the square root piece by piece. As x goes to infinity, 2 doesn't change, the square root is still there. So we have 2 plus 0, that goes to 0, over 0, minus 3. That simplifies to negative root 2 over 3. Any questions about that first limit? So this step in simplification is, well, it's definitely not something we've seen. Yeah. Okay. Now, how about the limit as x goes to negative infinity? Well, there are 2 ways you can do it. You can use an argument like that. the textbook, this is technically section 4.6 where they talk about horizontal asymptotes. The textbook does it using an argument like this directly from the beginning. Sometimes that causes a negative to show up. Because of that sometimes, I don't like to do it like that. Because of that sometimes, I treat the limits as x goes to negative infinity, as I described earlier, by converting it into a limit as x goes to positive infinity. So let's take a look at the conversion. Limit as x goes to negative infinity, 2x squared plus 5 over 4 minus 3x. Well, first, convert it into a limit as x goes to positive infinity. If you do like the other way where negative sometimes shows up there, you're certainly welcome to do that. First, convert it here into a limit as x goes to replace all x's with negative x's. So on the top, negative x squared is just x squared, so the top doesn't change, but the bottom does change because negative 3 times negative x is positive 3x. This equal sign applies to up there. That's a little line. Make it a little less. Any questions about that first conversion? So now we're back in this step. Largest exponent on the bottom is 1. I'll show this. Largest exponent on the bottom is 1. Multiply by 1 over x to the first. Divide by 1 over x to the first. You get the limit as x goes to infinity. Remember, to get that numerator 1 over x into the square root, we treat it as the square root of x squared. Slightly better. So treat the 1 over x as 1 over square root of x squared in the numerator, as we did up here. But notice now the denominator with the distribution is 4 over x plus 3. As x goes to infinity, this goes to root 2 plus 0 over 0 plus 3, which is root 2 over 3. And notice the positive infinity, negative infinity asymptotes or limits are different. So this function has 2 horizontal asymptotes. So y equals positive or negative root 2 over 3 are the horizontal asymptotes. Any questions about that one? Now, in this one, we had a degree 1 in the denominator. I'm going to write another one that you can work on, and I'll post the solution, I don't know, tomorrow, I guess. So maybe today. I already wrote up the solution. So as another example, similar to this one, where we have 2 different limits as x goes to positive infinity, negative infinity, consider find the horizontal and vertical asymptotes of this one. Root 3x to the 6th plus 1 over 2x cubed minus x. And I will post solutions to this later today. So any questions about what we covered with vertical horizontal asymptotes. Okay, let's do, we have a couple other, well, we have two what I would consider small topics next, and then a larger topic. So let's discuss the two smaller topics first, and then discuss the larger topic. The larger topic will be our last direct application of limits. But let's look at continuity. Continuity, an application of a limit. Now, well, let's define it first. A function is continuous at a point. This is going to be a couple sentences, maybe one sentence. A function will be continuous if you can draw the function essentially in one piece, meaning if you can draw it without lifting your writing implement. So like this one, you can draw that without lifting your writing implement. But what does that mean with limits? Well, let's take a given point. Let's take that point. What does it mean for us to be able to go through this point without lifting our writing implement in terms of limits? Well, it means what happens over here is the same as what happens over here, but also there's no hole there. You know, in our second graphical limit from actually last Thursday, there was a hole there, and then the point was actually up there. To draw that, we need to lift our writing implement. So here, for this function to be continuous at this point, for us to draw through this function without lifting our writing implement at this point, what happens on this side has to be the same as what happens on this side, and it has to be the same as the point between them. So what does that mean? Well, it means the limit is whatever that y value is. I think I used a in my notes. Yes. The limit as x approaches a is some y value, but it's also the function evaluated at a. So let's write that down. F of x is continuous at a point x equals a. I'll say f of x is continuous at a if the limit as x approaches a of f of x equals f of a. Our limit definition assumed only finite values, meaning no infinite values. And I'll illustrate that more with an example now. So right here, this definition, f of x is continuous at a point a. Well, that tells us that it's continuous at a, if the limit equals the function at that value. But for it to be continuous everywhere, meaning for the entire curve to be drawable without lifting your writing implement, this will have to happen at all points. This a should have been under that. From over there, it looks like it was under that. For it to be continuous everywhere, this must be satisfied at all possible choices of a. So I'll define that now. I'll just say and f of x is continuous if f of x is continuous. Sentence will get a little better soon. Before making the sentence better, this first definition says what it means to be continuous at a point. F of x is continuous at a. this second part is just a function being continuous. A function is continuous if it's continuous at all points in its domain. So I'll just say at all points in its domain. F of x is continuous if it's continuous at all points in its domain. So we have here what it means for a function to be continuous at a point and what it means for a function to be continuous on its domain. Well, should we do that first or this first? Let's do this first. Remark. One thing we will do is check whether a function is continuous at a point. Well, we'll check whether it's continuous on its domain, and to do that, we'll check whether it's continuous at a point. So to check whether, I don't like the word whether there, that'll change the sentence. To check for continuity, the noun form of continuous. To check for continuity at a point A, we must do what? Well, for a function to be continuous at a point, it must satisfy that definition. Well, we know from a previous theorem when the limit exists. A limit will exist, as we described over here, if what happens on both sides is the same. So if what happens on the left is the same as what happens on the right, then the limit will exist. So to check for continuity, we must check I'll just say whether the limit on the right equals the limit on the left. We want that to equal the function at the point. So this is kind of extending the definition using a previous theorem. Now, with that line, with that remark, there are a couple ways in which continuity can go wrong. Meaning the first equal sign may not be true. The second equal sign may not be true. The third way it could go wrong is if something goes off to infinity. So let's, before looking at an example of continuity, well, an example where we force continuity, I should say, let's look at ways in which this can go wrong with a graph. Example. This graph, well, if a function is continuous, or if this is satisfied, a function is continuous. If this is not satisfied, we'll say the function is discontinuous or not continuous. So this graph will illustrate how that can go wrong. So this graph illustrates discontinuities, possible discontinuities. Possible discontinuities. Get that spelled right. Well, let's look at 3 possible discontinuities. Let's move the y-axis over. So this is going to be a function. that. Let's put some y values and x values. Let's call this x value 7. Let's call this x value 5. Let's call this x value 1. Let's call this y value -2. Let's call this y value, I don't want to use the positive, so let's call it 4. Let's call that y value 6. Oh, I need another. Let's call this y value up here 8. Let's take a step back to make sure everything is reasonably online. Okay, so here we have a function. Let's call it f of x. Let's write it there so it's out of the way. Well, from our previous observation, from the informal definition I didn't write, a function is continuous if you could draw it without lifting your writing implement. So here, there are a couple places in which you can't draw the function without lifting your writing implement. At x equals 1, you jump from here to here. At x equals 5, you have to go up here and draw that point before continuing. And at x equals 7, you have to break off at infinity. So this function has 3 points, 1, 5, and 7, at which our function is not continuous. Let's describe them using this equation. So let's start at 1. Fit this on this board. I'm going to erase the word discontinuities because I'd like to fit this all here. And I'll just squeeze that there. So at x equals 1, what goes wrong? Well, the limit on the left does not equal the limit on the right. The limit on the left is 4. The limit on the right is -2. So at x equals 1, the limit write this. Okay, let's write it a little differently. Sorry if I already started writing that. Here, f of x is not continuous. As I said before, at x equals 1, at x equals 5, and at x equals 7. Let's write it like that, and then let's describe. So just from our lifting the writing implement observation, it's not continuous at these points. But what happens with this equation to prevent the function being continuous? Well, at 1, the limit on the right and the limit on the left differ. So at x equals 1, the limit as x approaches 1 from the right does not equal the limit as x approaches 1 from the left. That's just the end of the parentheses. So the limit on the right is -2, the limit on the left is 4. What goes wrong at 5? Well, at 5, notice the limit on the right does equal the limit on the left. So the limit exists and is 6, but f of 5 equals 8. So at x equals 5, I'll just say the limit as x approaches 5 does exist. It's 6, but it doesn't equal f of 5. So at x equals 1, this first equal sign went wrong. At x equals 5, that second equal sign went wrong. I guess I'm not going to fit the third sentence over there. Any questions about what went wrong at 5? Okay. what goes wrong at x equals 7? Well, at x equals 7, the limit on both sides happens to be positive infinity, which is not a real number. So there are a couple ways you could say. You could say limit on the left. I'll say it like this. At x equals 7, limit as x approaches 7 from the right. I'll say it like this, is not finite. The fact that it's not finite means the limit is not going to exist, because our definition of a limit not existing is that it's a real number. And I'll introduce some more notation to make the sentence not two sentences. The limit on the right or the left could be infinite. So I'll say that like that, the limit on the right or the left with a positive or negative on top of the 7. Any questions about that? So we have here 3 different types of discontinuities. I think it's pretty important to be able to see these discontinuities by describing their limits. Sometimes in math, you will see these described just in words, meaning this first one is sometimes called a jump discontinuity, because the function, in a way, jumps from here to here. The second one is sometimes called a removable discontinuity, because there's just one point where it goes wrong. And the third is sometimes called an infinite discontinuity. I'm not too concerned with the words. I'm much more concerned with being able to describe them with limits. Any questions about that? Okay, so let's discuss a little more about continuity before doing an example. All functions we have seen, all of the algebraic functions we've seen, all the transcendental functions we've seen, meaning like the sines and the cosines, tangents, exponentials, logarithms, all of them are continuous on their domains. So I'll say polynomials rational functions. This is functions. Excellent. Polynomials, rational functions, root functions. Function is a long word. I'm just going to abbreviate function with a capital F like that, because I'm going to have to write it like 6 times. Polynomials, rational functions, root functions, trig functions, logarithm, I guess exponentials at first, exponential functions, and logarithmic functions. Are continuous on their domains. So all functions we see are continuous on their domain. So, like with a root function, all you can have is the case when what's inside the square root is positive or 0. So it's not continuous where it's not defined, but it is continuous where it is defined. We'll look at an example of that in a moment, but let's cover another result. So say you have a rational function plus an exponential function, and you want to know if it's continuous. Well, it is continuous by this theorem. I'll say the sum and product, the sum and product, yeah, I guess singular, of continuous functions is continuous. Now again, continuous on its domain. In a large sense, saying a function is continuous implies by that first theorem just continuous on its domain. So if we have a x plus sine of x, a polynomial plus a trig function, well, that's going to be continuous on its domain, which happens to be everything. Working with continuous functions in many ways is more convenient than working with non-continuous functions, especially as we get into our next week topics, where by those two theorems, pretty much everything we see will be continuous. But let's just look at an example of finding where a function is continuous. Example. Let's do 2. F of x equals, let's do x squared plus 1 over x minus 5. Where is this continuous? It's a rational function. Where is this continuous? Well, it's a rational function. It's continuous on its domain. The domain of a rational function is everywhere except where the bottom is 0. Bottom is 0 and x equals 5. Any questions about part A? Look at this one, x sine x. Here we have the product of continuous functions. X is continuous, sine is continuous on their respective domains. So this is continuous on its domain. Domain of sine x, remember from our graph from week 1, is everything. Domain of x is everything as well. So this function is continuous everywhere. So on the entire real number line. Any questions about that? So let's do 2 more things with continuity. Find the value a, which makes f of x continuous at x equals -4. I'll need to give you a function. Here we have this function. We have piecewise function. It's defined in pieces. It's defined as some polynomial on the left of -4 It's defined as some other polynomial on the right of -4. And what we want to do here is force them to be equal at -4. So with limits, we want the limit on the right to equal the limit on the left at x equals -4. So let's do that. Let's first find the limit on the right of -4. I guess we should find one on the left first, since I wrote left first. Let's find the limit on the left of -4. This function is 4x squared minus 7 on the left of -4. So we have 4x squared minus 7. To find this limit, we can use our limit laws, let x equal -4. You get 4 times -4 squared minus 7. -4 squared is 16. 4 times 16 is 64. 64 minus 7 is 57. And what we want to do is force this to be the same as the limit on the other side of -4, the right of -4. On the right of -4, the function is defined as 2ax plus 3. By the limit laws, let x equal negative. By the limit laws, we can let x equal -4. If x equals -4, and be careful with this that you're actually letting x be -4 and not a. Sometimes when I do these and I rush myself, I substitute for a and then I have to go back and fix that. But here we're letting x be -4 because we're taking the limit as x goes to -4. Let x equal -4. 2 times -4 is -8. So this limit is -8a plus 3. So this function will be continuous at x equals -4 when what happens on the right is the same as what happens on the left. Well, two things are the same when they're equal. So 57 equals 8a plus 3. Subtract 3. Divide by 8. (54) divided by 8. Those are both even. 54 divided by 2 is 27. 8 divided by 2 is 4. That no longer reduces. Any questions about that one? Let's do one more. Let's make one more observation about continuity. Right. Where we are now, there are many limits we can't take. But when we have continuous functions, we can take some limits. So if f of x is continuous at, let's say, capital L, and limit as x approaches a of g of x equals L, then we'll see in a moment other limits we can take. There are some limits we right now can't take. But with this result, we can take limits of compositions of functions. I'm going to write that a little smaller. It's actually going to be a 3-part equation. Then the limit as x approaches a of the composition equals this limit. when f is a continuous function, you can push the limit inside the continuous function f. And then you can take the limit. Now, what does this mean? Well, this is a lot of math notation, but I think it's most nicely illustrated with an example. So what are we actually doing here? Well, let's look at this example. Compute this limit. Limit as x approaches pi over 2 of cosine of x minus pi over 2. Compute this limit. First of all, we have not computed a limit of a cosine function. We'll see how we can do that in a moment. But this result tells us we don't have to compute the limit of a cosine function. Cosine is continuous, at least on its domain. So we can push the limit inside that exterior cosine function and then take the limit. What does that mean? Well, it means we can do this. And another reason I like unlined paper is because I can exaggerate parentheses for organization purposes. So by that theorem, we can push that limit inside the cosine function. We can push it across the cosine. This limit inside, we can compute with the algebraic limit laws. Equals the cosine of pi over 2 minus pi over 2. So the cosine of 0. What is cosine of 0? Well, when I took calculus and my first 5 years of grad school, I didn't have the trig functions memorized. Now that I've taught Calc 1 a few times, I do have it memorized. But say you don't have the cosine of 0 memorized. Well, that point is 1, 0. Cosine is the x value. So that limit is 1. Now, what does that result tell us? Well, just like with the algebraic limit laws, it's convenient to not have to consider the details of the algebraic limit laws. And what this theorem allows us to do is treat a function like this as a direct substitution. So no, I'm never going to ask you to illustrate the theorem. But yes, I may ask you to use the theorem, and in that case, you can consider it a direct substitution type problem. So any questions about that? Okay. Let's cover one more topic. Right now, well, we'll cover two more topics, but to do two, we have to do one first, and then the other. Right now, we have not seen how we can compute just trig limits. In this one, we didn't take the limit of a trig function because the theorem allowed us to treat the limit separately and then evaluate the trig function. So let's prove a result on the trig functions. Well, yeah, okay, let's prove a result on the trig functions. To do that, we need another result. If you're following along the worksheet in any way, to this point, there's one problem on the worksheet, part A, that you can't do. But with this theorem, called the Squeeze Theorem, You can. So what does the squeeze theorem say? Well, let's state the theorem and then let's use the theorem. Let f of x be less than or equal to g of x. Let g of x be less than or equal to h of x. So we have three functions. One is smaller or equal to first, or one is smaller than the next, and that's smaller than the next. So we have three, in a sense, stacked functions, where smaller could also suggest equal. Well, this theorem says if the limit as x approaches a of the lower function equals the limit as x approaches a of the highest function, and they equal some finite number, call it L, then what happens? Well, before writing its punchline, what does this look like? Well, we have three functions, one's larger than the next, but at a point A, let's mark off A, the limit of the lower one and the limit of the highest one, limit of the lowest and the limit of the highest is L. So let's draw a potential f of x. Okay, so right here we have a potential f of x. Let's say it actually goes through A like that. So here's f of x. Let's draw an h of x. Let's use a different color. Somebody took my red chalk. Did they, or is it red? Oh, there's the. Let's draw a potential h. H is above f. Let's put it way above f, but the limit as x approaches a of h of x is still L. So right here, we have a setup for the squeeze theorem. What conclusion can we reach? Well, what we know is that g of x is between f and h. So let's draw a g of x between f and h. Well, what can we conclude? Well, at this point A, g of x is squeezing between f and h. So in particular, the limit as x approaches a of g of x is also L. Any questions about the statement of the squeeze theorem? Okay, so let's do a couple examples. Let's do 3 examples. Yeah, let's do 3 examples. 2 of them will set up algebraically. 1 of them will set up geometrically. Evaluate each limit. A, limit as x approaches 0 of x cosine of x. Part B, limit as x approaches 0 of, let's do x times the sine of 1 over x squared. That's So we have 2 limits. Now, first one, you may be tempted to try a direct substitution. You'd get 0 times 1, which is 0. To be completely technical, we don't have substitution for trig functions yet. but we will in a moment. So let's look at part A if we didn't have substitution. How can we do that? Well, we can use the squeeze theorem. For the squeeze theorem, part of the assumption, one of the assumptions is that you have a lowest function and a highest function. Because of that, trig functions are very convenient for squeeze theorem because sine and cosine have largest and smallest values. Sine is between -1 and +1. Cosine is also between -1 and +1. How can that help us? Well, let's see how it helps us. Our first observation is that cosine of x is between +1 and -1. Does that help us? Well, it might help us. We don't want the limit of cosine x. We want the limit of x cosine x. Let's make this look like x cosine x. How can we do that? Well, multiply the middle by x. Well, we can't just change equations. If we do something to one side, we have to do it to all sides. Multiply the middle by x so that that function is here. -1 times x is -x. 1 times x is x. Now, does this help us? Well, the squeeze theorem tells us that if the limit over here equals the limit over here, then the limit in the middle is the same. We want the limit as x approaches 0. What happens on this side as x approaches 0? What happens on this side to x as x approaches 0? Well, as x approaches, I'm going to introduce some more notation to ease the writing. So you could say, since limit as x approaches 0, x is 0, and this. I'm going to abbreviate that with an arrow. A large arrow could indicate a limit. As x approaches 0, what is this limit? Well, as x approaches 0, x approaches 0. How about over here? As x approaches 0, what does -x do? Well, as x approaches 0, -x approaches 0. Technically 0 from the negative side, but 0 from the negative side is the same as 0 from the positive side. So as x approached 0, the limit over here is 0, the limit over here is 0. So by the squeeze theorem, the limit in the middle is 0. So the limit in the middle is 0 by the squeeze theorem. In maybe 5 minutes, maybe a little more than 5 minutes, we will have, for one like this, that you could do a substitution. So for part A, in 10 minutes, if you had part A, you could do a direct substitution, but here we can illustrate the squeeze theorem. Any questions about part A? What about part B? Well, if you had a substitution, what would you get? 0 sine 1 over 0. This doesn't exist. Well, this is not a number, I should say. Because 1 over 0 is not a number. 1 over 0 is undefined. So even if we had substitution for part B here, it wouldn't help us. But what can we do? Remember, the limit doesn't care what happens at 0 in this case. Sine is always, where it's defined at least, is always between 1 and -1, just like cosine is. Sine is always between 1 and -1. And technically, sine of 1 over 0 doesn't exist. But this limit doesn't care what happens at 0, it cares what happens close to 0. So using that observation will or can help us. Well, just like before, we have this function. The limit we want is x times that function. So we can multiply everything by x. If you multiply everything by x, now the limit we want is in the middle. So if the limit over here is the same as the limit over here, then we can use the squeeze theorem to find the limit in the middle. Well, we want the limit, again, as x goes to 0. As x goes to 0, that goes to 0. As x goes to 0, that goes to 0. So by the squeeze theorem, the limit in the middle is 0. So limit x to 0, x sine over x squared equals 0. By the squeeze theorem. And you can see in this example, if I made this like an x to the 5th instead of just an x, the same type of argument would work. Any questions about that? So if a squeeze theorem question showed up on a test, which odds are it will show up on either the first test or the final or both, it is certainly more likely to be like part B than part A. But let's look at another application of squeeze. Let's look at another way we can reach to use the squeeze theorem. You're going to need a set of inequalities like this, where the limits on the left and the right are the same. Let's look at another way we can find such an inequality. Let's call this theorem. Limit as x goes to 0 of sine of x equals 0. Let's show this, and we'll use the squeeze theorem. Now, with this theorem and the two observations we'll make afterwards, and the continuity theorem we covered, we will be able to treat trig functions. We will be able to treat limits of trig functions as direct substitutions. But why is this true? Well, let's see. Right here, we have the unit circle, and I'm more magnified in the first quadrant because that's where we're going to look. Unit circle, circle of radius 1. The 1 will show up somewhere. Now, why do we use radians? Well, one reason we use radians is because the radian tells us not the angle. Well, it tells us we can use the angle, but using the radians for the unit circle relates the angle to a segment on the unit circle, to an arc on the unit circle. So if we have angle theta here, then, and theta is in radians, then the length of this arc of the circle, since it's radius 1, is also theta. So this length is theta by the definition of radians. You could also use that, the formula for arc is what, radius times angle in radians, I think. Use that in this class. But right here, that has length theta. Why does that help us? Well, We can also see, we want sine of x, we can also see sine of x in this diagram. Maybe I should have made that a different color. We can also see sine of x, because remember, for this point, the x value is cosine of x, and the y value is sine of x, or sorry, sine of theta. We have angle theta. The x value is cosine of theta. The y value is sine of theta. While the y value is the height from the x-axis. So that red line is sine of theta. Any questions about that diagram? Okay. Now, can we find a Squeeze theorem equation from this? Yes, we can. From the diagram. Well, sine of theta is a vertical line starting at this point. Theta is an arced line starting at that point, and they both go to the x-axis. So sine of theta, that vertical line, is smaller than theta, that curved line. And these are both greater than 0 or equal to 0. Any questions about getting that equation? Okay. So in the theorem, I guess I have x's here, I have thetas, and you can get the theorem just from replacing variables. Throughout the semester, we'll deal with x more than theta, so I wrote the theorem like that. But when the angle is actually marked, I usually use theta. We want to know what happens as this variable goes to 0. Well, as this variable goes to 0, over here, 0 doesn't change, so 0 goes to 0. Over here, as theta goes to 0, theta goes to 0. So the limit as theta approaches 0 of this middle function sine theta is 0 by the Squeeze theorem. Any questions about that? Well, before any questions, I will not ask you this one. So any questions about this one? And this is more to illustrate another way we could see the Squeeze theorem. Now, well, there's a conclusion about sine. So from this, well, we have a nice relation that sine squared plus cosine squared equals 1. From this, we can conclude the limit of cosine x as x goes to 0 is 1. Why? Well, I'll just write a small proof here. Why? Well, we can write cosine in terms of sine because sine squared plus cosine squared equals 1. If sine squared plus cosine squared is 1, then cosine squared is 1 minus sine squared. So cosine is root 1 minus sine squared.
Do we have to know this proof?
You don't. And then there might be other contexts in which sine squared plus cosine squared equals 1 shows up. In Calc 2, sine squared plus cosine squared equals 1 shows up a couple times. Calc 1, it really doesn't show up much. Cosine is root 1 minus sine squared, and then you can use the limit laws here to conclude that this limit is root 1 minus 0 squared, 0 from that, which is 1. So we can reach the conclusion about cosine. We can also reach the conclusion about tangent. So I'll say also limit as x approaches 0, tangent x does equal, well, notice with the cosine, substitution would give us 1. Right there is a proof for why it would give us 1. And up here, we can do the same with tangent, because tangent is sine over cosine. Tangent is sine over cosine. The limit laws say we could do the limit on top, limit on the bottom. From that, we have 0 on top. From that, we have 1. You get 0 there. So right here, yes, I will not ask you to prove any of these 3 statements, but from all of this, we can, from all of this and our resultant continuity, we can treat trig limits as substitutions when substitution works. Any questions about that? So for these last 20 minutes, we will introduce the derivative. What is the derivative? The derivative is an application of limits. It's the last application of limits that will look like applications of limits, at least for today. So calculus is largely, calculus 1 is largely broken into 3 pieces. There's the limit, the derivative, the integral. The derivative and the integral are technically limits. So to define the derivative and the integral, we need limits. We will start with the derivative. And let's see, this is a 6-week class. Weeks 3 and 4 will be 100% devoted to the derivative and applications. Part of week 5 will be devoted to the derivative. And, well, the last part of week 2 is devoted to the derivative. So that right there makes up a little more than half of the semester. So the derivative is very important in calculus. It's in many ways what calculus is all about. What is the derivative? Let's spell derivative right. What is the derivative? Well, let's draw a couple graphs. Right here, there are going to be 4 graphs drawn side by side, so you know for note-taking purposes. Let's make it look like that. There's a function. Here, I'm going to mark off 2 points. I'm going to call this one A. I'm going to call this X. It's going to be 4 graphs. I would like to draw this under. I could lift this up a little. Well, actually, no, I'm going to erase this title of the derivative. So in your notes, it's a good idea to write in large letters somewhere, that this begins the derivative. But these boards aren't that tall, so I want all the space. So here we have a function, here we have a point A, here we have a point X. There's A, there's F, there's a function. And I'm going to write something under that, and I'm going to do the same thing here, but A is going to be fixed in all four of these graphs. X, I'm going to move around on these graphs. X will be a variable quantity. That's So we have four curves. They're all supposed to look about the same, even though that last one does look a little bigger. But let's start with the first one over there. We have 2 points marked up. What we're going to do is draw that line between those 2 points. Why are we going to do that? Well, we'll see why on graph 4. That line containing those 2 points on the curve is called a secant line. You don't really need to know the word secant too much for this, especially once we get to the fourth one. But we can find the slope of that secant line because we have 2 points. Given 2 points on a curve, we can find the slope. So we'll call the slope of that line m sub sec, slope of secant line. And what is that slope? Well, it's the y change divided by the x change. The y value for this point is f of x, the y value for this point is f of a, divided by the x change. Divided by the x change, x minus a. Any questions about that slope of that line? Well, one thing, well, what we're going to do with this line, in that first case, for that first function, these are all f of x, I chose x pretty far away from a. But what happens as we let this x value get closer to a? Well, let's move x, let's do a little closer than that. Let's let x get a little closer to a. Well, what happens to that secant line as x gets closer to a? Well, it's still a line through those points. Still a line containing those 2 points. Let's let x get even closer to a. Move x over there. Still a line containing those 2 points. And because of that, there's still going to be a small gap between the line and the curve. You know, this wedge-like type piece is still going to exist in these two. It's getting much smaller, but it will still exist. But as x approaches a, meaning if we take the limit in this x movement toward a, what does that line approach? That line will, instead of going through the 2 points, as x gets infinitely close to a, meaning if we take the limit in that x movement, that secant line is going to approach a line which hits this curve at only 1 point. Maybe I should draw that tangent line a little better. Right here, it looks like there's a gap because of how large I drew a point. Here we have a point. Take the limit, let x get arbitrarily close to A. And this line now approaches a tangent line, meaning a line which intersects the curve f of x at exactly one point. So we have that tangent line. And the derivative is going to give us the slope of this line. Now, how can we describe the slope of this line? Well, we can describe the slope of the secant line in all of these cases. But over here, all we're doing is taking the limit. Maybe I should have labeled this secant line since I labeled that tangent line. So secant line, that's a lot of arrows. The secant line approaches the tangent line in the limit. So what is the slope of this tangent line? Well, let's call it m tan. Slope of that tangent line, well, it's the limit of the slope of the secant line. Which limit? Well, we're taking our x value, our variable x, and pushing it toward A. So it's the limit as x approaches A of the slope of the secant line. What is the slope of the secant line? Well, we can just replace the slope of the secant line with the equation over there. Is that written on the board? Yeah. Any questions about these diagrams? Our goal with this was to find the slope of this tangent line. And to find the slope of this tangent line, we recalled that to find the slope of a line, we needed 2 points. But combining that with a limit gives us the slope of the tangent line. Any questions about that? So right after that, I'd like to just make one observation or one remark. Then we'll continue with this remark. This remark references that last equation. This, meaning the previous equation, gives the slope of a tangent line at the point A. That right there gives us the slope of the tangent line at a given point A, that limit. It would be nice if we had a function which gave us the tangent line at any point A. Well, we can do that by changing this into a function. How can we do that? Well, let's do it like this, and then let's define it. That's the phrasing I used over here. Well, let's do it like this. Let's we would like to have a function which gives us the slope of a tangent line at any point, meaning we would like this a value to be variable. In that previous discussion, the x value was variable and the a value was fixed. So to give us a function which will give us slopes of tangent lines at any x value, let's introduce an alternative notation. Let's call this alternative notation. We will use that first definition once next week or something. We'll use this next notation much more than that first notation. Alternative notation. Instead of letting this value over here be x, let's write this value over here in terms of a. Meaning, this a is an x value. It's this x value, whatever that distance is. So this other x value is this a plus some other distance. Let's call it h. So if this value is a and that entire thing is a plus h, then this distance between them is h. But with this relabeling, we can rewrite the slope of the tangent line in another way. So here, m tangent equals what? The limit. Which limit? Well, let's write our equation first and then we'll write the limit. The change in y was, there is f of a plus h minus f of a, and it's all divided by change in x, a plus h minus a. Now this may not look more simple. It actually is more convenient to work with in many cases. The first example is more convenient to work with in a couple other cases, one of which we'll see. But which limit is this? Well, remember, we're pushing this x value toward this x value. So here, we're going to let a plus h approach a. Now, let's simplify all of this. Well, since we've broken down our x-axis into an a value and this h value, we can describe that limit as letting this distance here go to 0. Letting that distance there go to 0. What happens if we let that distance there go to 0? Well, this x value is going to approach that x value. And how does this fraction simplify? Well, the numerator doesn't simplify at all. But the denominator, a minus a, is 0. So the denominator simplifies to just h. So right there, we have another way we could write the slope of the tangent line. And this second way we will use more frequently than the first way. But let's right now define the derivative. What we mean by the derivative. Definition. Let f of x be a function. The derivative of f of x denoted f with a kind of a big apostrophe, f prime of x. So it's a kind of a big apostrophe, read f prime of x, is given by the following limit. Limit as h approaches 0. We're going to take that definition and let a be variable so that it will give us the derivative at any x value. So our goal was to find what the following remark is going to describe. So we'll define the derivative like that, and let's just make a remark on what this actually means. Remark. Now, to remark, remarks in math are generally used to clarify something that may be a little more unclear than it should be. So this remark will make this definition a little more clear, hopefully. F prime of x, it's a function of x, is the function that gives the slope of the line tangent to f of x at any x value. So we will see that this definition has many applications. Being able to find slopes of tangent lines allows us to reach many, many conclusions. Any questions about that? Okay, well, it's 3 o'clock, so we will stop this here, and because we're stopping this here, I'm gonna have to change what to show up on the test. So since we're stopping here, I was hoping to get through at least one example of this. So the parts that say anything about definition of the derivative in that email aren't going to be tested because we didn't actually use it yet. We'll cover this next week. But also, you may push these off until next week. Worksheet 2, problems 7 and 8, you can skip those for now. And also homework 4 or homework 2, problem 4. Now we'll do that next week. So if you already did homework 2, problem 4, that's fine. I'm going to push that on next week's homework. I'll write it on homework 3. But for this week, since we didn't actually use the derivative definition, you can skip 7 and 8 on the worksheet. You can skip problem 4. I will write this in an email as well. And these problems will be, just copied and pasted onto the worksheet I post next week. Now in the schedule, I did work a little bit of, in case something took longer to cover than other things. But also on the test, there will not be anything with the definition of the derivative. So the test, for notes purposes, the test will stop at the end of our squeeze theorem discussion. Any questions about anything? And everything I did just say, I will write in an email to you at some point. Hopefully today, but sometimes I, don't finish writing an email till 10 o'clock and they don't like sending things that late. But any questions? Okay, well, I hope you enjoy your week. There is homework due tomorrow, just numbers 1, 2, and 3. And I do recommend submitting that closer to tomorrow than after tomorrow, just because of exam preparation. So